Good morning and welcome to your learning. Thank you for showing up. Let's take a look at this kooky looking function. Isn't this kooky looking? It's like a parabola, except it's got a squiggle in it. Where does it get that squiggle? Well, this is x squared plus a sine wave, sine of 3x. So it's actually adding that squiggly sine wave to a parabola, and it allows us to see the transformations really beautifully, this cool function that Desmos has cooked up for us. Now here is a transform function. G of x is a times f, a times the output of the function, and k times the input of the function. So if I take this slider a, and you'll notice that the two functions are different colors, what do you predict is going to happen as I start making a larger? Camden, what will happen? Nice and loud for the microphone.
Will it get more compressed?
If I make a
Or
larger,
smaller? Never mind. It'll get thinner.
it's actually going to grow bigger. Notice that the position of the squiggle stays in the same place, but now if I make a 2, the squiggle is now 2 times higher, right? Like this point was like a little bit more than 1, now it's a lot more than 2. So it's gone 2 times higher. It's being, how would you describe that using the English language?
Thinner.
It's what's happening to it in the vertical dimension?
Stretch.
It's being stretched in the vertical dimension. What about if a becomes very close to 0?
Compressed.
It's being compressed vertically, yeah. What would happen? What do you predict is going to happen if I set a is equal to -1?
Reflected.
What's going to happen if I make a -1? Where's the reflect? What's going to happen? It's going to just flip over. Eh? That's a good way of talking about it. Through what axis? What's the axis of flip over? What's the axis of reflection? The x-axis. It will reflect in the x-axis. So there you see nice and clear this reflection in the x-axis. Good. So now let's take a look at k. So I'm going to make a equal to 1 so that we don't have to worry about the role of a in these transformations. When a became bigger, it became stretched vertically. What happens when k becomes bigger? Also, Jacob. Is it going to stretch horizontally as I make k bigger? Let's make k bigger. Oh my gosh, what's happening? I'm getting so skinny. Look, k went up to 10 and the function got super skinny. What happened to it? It got squeezed. It got squished. It got compressed. In what dimension? In what dimension did this squeeze happen? Sorry?
Y.
It got squeezed towards the y-axis. It got squeezed horizontally. It's like pancaked towards the y-axis when k becomes big. Now look, see this point here, this like little point there? It's like a little bit bigger than 1. And then over here, this point is like, oh, look at that, 0.125. Over here it was 1.25. Now it's 0.125. It's now 10 times closer to the y-axis. It was squeezed horizontally by a factor 10. What will happen as k approaches 0? What do you predict is going to happen if k is less than 1 but bigger than 0?
It'll be compressed on the horizontal.
Now it's going to be stretched horizontally. Look at that. K is 0.2, and now look at it. It's so stretched. What will happen if k is -1? Esme, what will happen if k is -1? In what dimension? What will you describe what you're seeing here? The black one is the transformed one. I tried Halloween-y colors. Aiden? Y-axis is now our mirror when we have a -k. So -k flips in the y-axis. So now let's so we've been investigating the roles of a and k in the transformations of functions. Now let's take a look at b and c. So Desmos already has these graphs made for you. They're pretty cool. If you go in here into this, it gives you all your saved graphs. I'm not logged in, so you can't see my saved graphs. So they've got beautiful ones in here for transformations of functions. Where's transformations t? There it is. Scale translations here. So these are translations of functions. They got the same function being translated. I'm just going to change the color of this one. So you can change the color of your functions by going there, there, and then say done. Okay, so now we have black and orange. So now I'm going to set, and they use H and K for their variables here. Isn't that annoying? We use D and C. They use H and K because they like to confuse us. No, that's not it. Because those are the coordinates of the vertex, and the vertex in vertex form of a parabola is going to translate around with our D and C or their H and K. Doesn't matter what letters we use. Same function. Now I'm going to set these sliders to 0. What do you predict is going to happen when I set these sliders to 0 if D is 0 and C is 0? What has happened here? It's just the same function, Mr. Jennings. You're adding nothing to it and you're adding nothing to it. So it's the same function. So when D and C are 0, they're not having any effect. So I have the function is x minus D plus C. What's going to happen as D grows larger? Camden.
Will it go? The function will move side to side.
Yeah, it kind of moonwalks. It kind of moonwalks over here. And as D becomes positive and I'm subtracting progressively larger values, it moves in the positive x direction. Moonwalks over there. If I go in the D negative direction, now I'm adding to the function. I'm adding, to the inputs of the function, because this is x minus 3.8. And I notice that, okay, here's minus 4. And the point that used to be the origin, 0, 0, has now moved over to negative 4, 0. So it moonwalks side to side when D changes. What about C? What role will C have if I'm adding to the outputs? Alina. Now it's going to float like a ghost upwards. So it's very Halloween-y today, so we're very thematic. And then if I want it to be like a zombie, so here it's a zombie and it's in its grave, and that's a negative C value. And then as C rises, oh, here comes the zombie. Here's its hand. Oh, its hand just came out of the ground. Oh, it's coming out to get us. And then the zombie comes, and now the zombie can walk on the ground and come and get us over here. Okay, so these are some of the things that the A and K, A multiplies outputs, K multiplies inputs. D is subtracting from inputs, C is adding to outputs. These are our 4 ways that we can transform a function. And they move the function around, they stretch it, they reflect it, they flip it, and they translate it around. So we want to be able to do multiple combinations of these transformations at once. So here is a quick intro. I said I would do this quick, and so we're going to start going quick. Let's say I have this situation where I had a function g of x, and then I want to take that. I have that function. It's a squared function. It used to be f of x, and now it's g of x. And to change f of x, this function x squared, into g of x, we're going to do the following things to it. It has an a here, a k there, a d there, and a c there. All right, so I just want to be able to identify those different numbers and think about what they will do to the function. The first one is this number here, negative 2. That will be negative, so it's a vertical reflection. It's going to reflect this parabola in the x-axis. So actually, we could follow along. Oops, I'm doing the wrong thing. There we go. Let's go to Desmos, and we'll graph it as we go. So let's get a fresh Desmos. Leave. Here is our original function, y is equal to x squared. First thing that we did was we reflected it in the y-axis, in the x-axis. And that's this negative here, 2. And then we're going to make it 2 times stretched. So there's our negative 2a. And then we also want to horizontally compress it by a factor 1/3. We're going to squeeze it towards the y-axis by a factor 1/3. If I'm doing that with a parabola, I actually need to have that right next to my x. Now I've squeezed it by a factor 3 towards the y-axis. Notice the effect of these brackets algebraically. Can you see that? Maybe not. So there. So notice the effect of these brackets algebraically. This is now 3x all squared. The 3 will be squared. It's like multiplying it by 9. So parabolas are a little funky in that a horizontal squeeze is the same thing as a vertical stretch. But if I squeeze by factor 3, it's the same thing as stretching by factor 9 in the vertical because of the effect of the squared. And that's only with parabolas. Parabolas have this. It's not that they're indifferent to k and a, but k and a have a similar function with a parabola. Okay, let's keep going. And now, so we've done these two translations where we have flipped it in the x-axis, we stretched it 2 times, and then we squeezed it 3 times towards the y-axis. Now we're going to translate it 2 units to the right. This is a horizontal translation, right 2 units, and then down 1 unit. So let's put those in algebraically here. We're going to go here 2 units to the right. That's the 3, Mr. Jennings. It's 2 units to the right, and then we're going to go down 1 unit. Okay, now let's take a look at our parabola here. Notice that the vertex has now been moved from 0, 0, 2 units to the right, and down 1. So that would be g of x. This is a now transformed parabola. You'll notice that it's naturally written. It's not naturally written. Why is that happening? I'm just going to zoom out. No, I'm really confused now as to what my fingers are doing on the keyboard. I don't know. I don't understand. I think I need to just refresh and not worry about that page again. I'm sorry. So anyway, it would now be written in vertex form after I've done all these translations on it. So let's take a look at some other examples. Here is the function f of x is 1 over x. And if I want to translate it in this way and transform it, I need to identify my a, my k, my b, and my d. So this here is going to be my stretch factor. It used to be 1 on top, but now we have 1 times 3. So now 3 times stretched vertically. I'm not multiplying my inputs by anything, so that k is 1. And then I'm going to be moving it 1 unit to the left by adding to the input. So that moves everything 1 unit to the left. And then I'm raising it 2 units up. So now let's go back to what we've been looking at this week. If I have this function here, f of x is equal to 1 over x, what's my limitation on x? What can x not be in f of x? X cannot be 0 because that would have a 0 on the denominator, so x is excluded from the domain. What about over here with g of x? What is x not allowed to be? Minus 1. Yeah, so the function has been translated 1 unit to the left. Now the asymptote has moved over. Let's graph both of these functions in a fresh Desmos, please. So we're going to go here to a fresh Desmos, leave and open. And there we have everything that we need. Okay, that's good. And we're going to zoom out a little bit. I don't know why this is so huge. There, that's a little better. Okay, so now we have y is equal to 1 over x. What is going on? There we go. Okay, that's a little better. And now we're going to zoom in a little bit. Oh, I think I broke Desmos, everyone. My apologies. Okay, so here is the function y equals 1 over x. Notice what's happening around that restriction. X is equal to 0. X cannot be equal to 0 because this function goes off to infinity before it hits that point. Now, if I take a look and graph the translated function, y is equal to 3 over x. That was our first translation, our first transformation, sorry. Notice that that stretched it 3 times vertically. Everything became a little bit bigger, all of the y values. And then we said this is x plus 1 on the bottom. Notice now, around this point, negative 1, that the function is going up to infinity and going down to infinity. It moved the asymptote 1 unit to the left. And then, I think we're adding 2 to it or something, are we? Yeah, plus 2. Okay. So now, when we add 2 to the function, Now y can't be 2. Before, y couldn't be 0. There was no way to make 1 over x be 0. Even with very, very large numbers of x, y is still non-zero. Here, it's no way to make this unit 0, so y can never be 2. Notice that 2 is excluded from the range. Yep. What's up, Diego?
I don't like. I can see what happened when like you guys did 2,
Mhm.
but I don't understand like the 3.
The 3. Okay, so let's remove these and we'll take a look at the 3 in isolation. So if I take a look at this point 1, 1, see it there? There's the point. The red one is the parent function. Yeah, let's graph the line x is equal to 1, and it'll give me some intersections. This was on the original function, the point 1, 1. And that should make sense because 1 is equal to 1 over 1. So that's why we have that point there. But then in this one, y is equal to 3 over x. Now if I put in 1 for my input, my output would be 3. See how it's stretched it vertically by factor 3. Everything has been stretched away from the x-axis like by being multiplied 3 times. All the y values are 3 times bigger. Okay. Now if I take a look over here at the point -1, -1, then I would have the point -1, -3 down here. Again, stretched by a factor -3. And now if I want, I could flip this in the y-axis and the x-axis as well, like this. -3x. See, that flips it in the x-axis. See what we did there? Yeah. Would also be the same. This one is indifferent to flipping in the x-axis or flipping in the y-axis. It'll be the same, because if I have the negative on top or bottom, it doesn't matter. So that's the same as having the negative on top. Okay, so let's get to our main point here. That way I can release you to do some work on your own and practice these on your own. So here, when we're graphing transform functions, this is one method to do it, but I want to talk about a different method looking at delta math. So I'd like you to start your practice with delta math today. So what are we getting at here? Oh, I don't have a slide for this. When we're applying transformations, what we want to do is make sure that we notice that here in this set of transformations, we did our vertical stretches and reflections, and then our horizontal compressions. We did A and K first, and then we do our translations. The reason for that is BEDMAS. BEDMAS requires us to do multiplication or division first, and then do addition and subtraction. A and K are multiplying either inputs or outputs. D and C are adding or subtracting from inputs or outputs. So do your multiplication transformation first, and then do your translation transformations. Yeah, we're not going to do a quiz on this tomorrow. It's too soon. It's too soon, Mr. Jennings, too soon. So let's take a look at how you can do the transformations of functions skills that we're practicing. So the first skills, I'll give you just a rundown on some of these questions, and you can take a look at how I approach them. So here we have the equation y is equal to the square root of x minus 5. They have been so kind as to graph the parent function for us. And all we need to do is now graph the function x minus 5. So I know that this will be a horizontal translation towards the right by factor 5. The reason is x minus 5. Now, if I had the point x is 5, notice 5 minus 5 is 0, so my output would be 0, so that's why it's moved over that way. I can take a look and go point by point and move my points, no problem. Here is the point in the parent function. Let me zoom in here. The point in the parent function, 1, 1. If I want to see what happens to that point, and I say, well, let's get an output of 1 there, I would need 6 minus 5 to create that one. It's the x value that would produce that is 5 over. So I'm going to grab this parent function, I'm going to move it over by factor 5, then I'm going to say, that's done, submit answer. And it says, are you sure? And I say yes, and it says, yes, you are right. Shift right 5 units. When I subtract from inputs, it shifts right. When I add to inputs, it shifts left. Now let's take a look at another problem. Here is x minus 5 cubed minus 4. We haven't taken a look at the cubic function, but that's what it looks like. And here we are shifting it right 5 units and down 4 units. So go right 5 and down 4. Notice that I grabbed the green button. When you grab the green one, that moves the whole function. If you grab the blue ones, that stretches the function. So don't stretch it, just leave it where it was. And then say submit answer. Are you sure? Yes, I'm sure. It says no. Shift right 5 units, shift down 4 units. What did I do? And I stretched it a little bit. You have not plotted the light red graph above represents your. Oh, it was slightly stretched. Yeah, it was slightly stretched. I made a mistake by stretching it a little bit. I did not. Yeah, don't stretch that. Okay, so that's how you do those. Now it's stretch compress functions. So we want to take a look. Here is the cube root function. The cube root function looks like the cube function on its side, and then it's by factor 1/2. So this would be a good function to stretch. Notice I can now stretch the function with the blue ones, and I can reflect it in the y-axis, or I can reflect it in the x-axis. It's really cool. You can play around in here. I know that it's being squeezed horizontally by a factor 1/2. It got 1/2 as high. So this point, which used to be at 8.2, is now at 8.1. And I can put it in there. It snaps to there. I say submit answer. Oh, no, submit answer. Yes, and yes, it likes that. Vertical dilation, it says here. So that's a different word than we usually use. This is vertical dilation or vertical stretch by factor 1/2. I like the word stretch, but dilation also works. You can think about how wide your pupils get when you see a great math question. See another one? 4x to the 3. So I can take this point and stretch it 4 times in the y-axis and say that's my new translated function. Okay, good. And then let's get one with a k. Yeah, I thought this would give me k's. This is just stretch compression. Reflecting functions. So reflecting functions here, I have a exponential function. This is our next unit. And it's being reflected. This is an a of -1 and a k of -1. So it's going to be reflected in the y-axis and then reflected in the x-axis. So that will be our new function there. Double reflection. Reflect over the x-axis, reflect over the y-axis. So try some of these practice problems. Here's the absolute value function. It's being reflected in the y-axis. So I would bring this down here. There we go. Submit answer. And do these reflections. Practice all of these different transformations. And then here are some transformations of functions with mixed transformations. So here it's being stretched by factor 1/8 in the vertical, and it's being reflected in the y-axis. So we could do the reflection first or the stretch first. If I reflect first, this point is 2.8. So it would reflect to 2 -8. And then I squeeze it by factor 8. So 8 would become 1. And then it snaps to the integer point. I graph the new function, submit answer, yes. So this is how we go through these types of questions and do multiple transformations. Let's see if we can get one that has some. Here's a good one. So here I have the parent function is x squared. They've graphed the parent function for me. That's beautiful. And I need to reflect it in the x-axis. So that's going to be a vertical reflection. And then it shifts 3 units to the right. So let's reflect this point. It reflects down to there to 1 -1, and then move it 3 units to the right. That's how you'll do these. Submit answer. Are you sure? Yes. And yes, that is correct. So if we see some of these with multiple transformations, here, the absolute value function. It's a vertical stretch by factor 3. I do that first. So let's take this point 2.2 and stretch it to 2.6. There's my vertical stretch. And now I want to move it 3 units to the left. Like that. Submit answer. Yes. Good. Good. And if we take a look at transformations of functions, now this one, these are different problem types. This one asks you what transformations are required to create the red dotted graph. So here I have the absolute value function. It starts at 0, 0, but the point 0, 0 has been moved to 5, -3. However, it has not been stretched, it has not been compressed, it has not been reflected in any of the axes. So I could say, well, one of these is going to do it. I want to subtract 5 from all my inputs and add -3 to all my outputs. So it looks to be, it's going to be there, this one here. Y is equal to x minus 5 because it moved 5 to the right. That's right on the video. And it went down -3. So it's this one. So there, that's this type of problem. Yeah. Uh-huh.
Can I go for my driving?
Yeah, absolutely. Yeah. So here we have 2 to the x. This one has been actually stretched. So if I take a look at this point, 1, 2, take a look at what happened to that point. It's now way down here at -8. So I go through and I find the transformation that would do that. And I can also say that this point 1, 0 has been translated over here to -2. See this point here, if I zoom in, this point there, the point 0, 1, if I flipped it, it would be down here. So it looks like I need a vertical flip, but then I move it over here by 2. So that's one way to create this. So I have made it negative, and I have translated it 2 to the left. So it's going to be this one here. This would be movement 2 to the left.
Thank you.
You're welcome. Am I right? Yes, I'm right. Yeah, so there you go. And then it does this nice thing where it says translate 2 units to the left. See it? It shows you the transformations. So you're going to be learning about exponential functions as well while you're doing this. That's going to help you get ready for next unit. Exponential functions are weird. They're fun. Okay, so those are some of the question types that you'll practice in the Delta Math to practice doing multiple transformations at once to different things.